Earth has a heartbeat. Every 26 seconds, like clockwork, the entire planet shudders with a faint, rhythmic pulse. And after more than 6 decades of listening, no one on Earth can tell you why. It isn't an earthquake. It isn't a storm. It isn't a machine, a submarine, a missile test, or anything humans have ever built. It is a quiet, persistent thump buried deep inside the seismic record of our world, ticking away beneath the noise of cities and oceans and continental drift. And it has been ticking since long before anyone noticed it. Geologists call it a microseism. The internet calls it the heartbeat. And the truth is, after 60+ years of studying it from every angle science has to offer, the most powerful experts on planet Earth have, more or less, given up trying to explain it. So how does a planet end up with a pulse? How does the ground beneath your feet, the bedrock you assume is dead and silent, develop a rhythm that runs steadier than any human heart? And why, in an age when we can image individual atoms and detect gravitational waves from colliding black holes a billion light-years away, can't we figure out what is happening on our own front porch? This is that story. The first person to notice the pulse was a geologist named Jack Oliver, working at Columbia University's Lamont Doherty Earth Observatory in 1962. Oliver was a careful man, the kind of scientist who trusted instruments more than intuition. And he was sitting with stacks of seismograph readings, the long, curling paper printouts that record the slightest tremors moving through the Earth's crust. He was looking for patterns. He found one nobody asked for. In the background of his data, behind the earthquakes and the ocean storms and the everyday noise of a restless planet, there was a tiny, regular tick. It repeated every 26 seconds. It wasn't loud, it wasn't dangerous, it was just there, always there, quietly hammering away at the bottom of every record he pulled. Oliver triangulated the signal as best he could with the technology of the era and traced it to somewhere in the Atlantic Ocean. Roughly. He published his observation in 1962, noted it as a curiosity, and the world moved on. The space race was heating up. Plate tectonics was about to revolutionize geology, and a small, repeating thump in the South Atlantic was, to put it mildly, not a priority. The pulse kept ticking. Decades passed. Seismometers got better. Computer modeling got faster. Satellites went into orbit. Telescopes were launched into space. And humanity catalogued an extraordinary amount of new information about the universe. And still, every 26 seconds, somewhere in the depths of an Earth observatory, that signal showed up. Steady, unchanging, ignored. Then, in 2005, a graduate student named Greg Bensen at the University of Colorado was running tests on a new seismic analysis technique. He was teaching a piece of software to identify weak signals buried under stronger ones. As a kind of accidental side effect, his work pulled the 26-second pulse back into the spotlight. There it was again, a rhythmic ghost humming in the data, exactly where Oliver had found it more than 40 years earlier. The thing hadn't moved. It hadn't faded. It had just been waiting. Bensen's advisor, Mike Ritzwaller, looked at the readings and thought there had to be a mistake. There wasn't. The team narrowed the source down with much greater precision than Oliver had been able to. The pulse was coming from the Gulf of Guinea, a stretch of the Atlantic Ocean curling beneath the bulge of West Africa. More specifically, it was coming from a single point in the Bight of Bonny, off the coasts of Cameroon, Nigeria, and Equatorial Guinea. That was the first surprise. The pulse wasn't drifting around the ocean like a storm or a current. It was coming from a fixed location, the way you might expect a buried machine to behave, or a heart. The second surprise was the precision. 26 seconds, give or take a fraction of a second, year after year, decade after decade. There are very few natural processes on Earth that maintain that kind of clockwork rhythm at that scale. Tides shift, storms come and go, earthquakes are random. Whatever this was, it had a pacemaker.
The third surprise was that the signal traveled far. The 26-second tick was being detected on seismometers across North America, Europe, Asia, on islands scattered across half the planet. Whatever was happening in the Bight of Bonny was loud enough, in geological terms, to ring through the entire crust. That takes a serious amount of energy, the kind you don't generate by accident.
Except this one, nobody could find a source for. So what could possibly produce a steady tick from a single spot in the Atlantic, lasting longer than most countries have existed in their current form? That's where things get strange. The leading theory points to the ocean itself. When deep ocean waves, the kind generated by storms across thousands of kilometers, slam into the continental shelf, they can deform the seafloor enough to send pressure waves rippling through the Earth's crust. The phenomenon is called microseismic noise, and it's why seismologists working in coastal regions hear a constant, faint hum even on a calm day. The Gulf of Guinea has a peculiar shape. It's a wide, shallow basin where the African coastline curves inward, and certain types of ocean swells, when they hit the continental shelf at just the right angle, could in theory bounce, focus, and resonate. If you've ever blown across the top of a glass bottle to make it whistle, you've experienced something similar. A specific shape, struck by a specific kind of energy, can produce a remarkably stable tone. The Gulf of Guinea, the theory goes, might just be that bottle. That theory has its champions. It explains why the pulse comes from one fixed location. It explains why it's been running so long. The theory has problems too. For one thing, there are coastlines all over the planet that should produce similar effects. Why doesn't the Gulf of Mexico ring like a bell? Why doesn't the Bay of Bengal? Why is this one specific corner of the Atlantic generating a signal strong enough to be picked up on seismometers thousands of kilometers away? Geologists have run the math on dozens of coastlines, and nobody has found another spot quite like the Bight of Bonny. The Earth tends to repeat its tricks. Unique features in geology are rare. For another thing, the pulse is consistent in a way ocean noise usually isn't. Storms come and go. Wave seasons change. The Atlantic in February is not the Atlantic in August. If the heartbeat were really driven by ocean swells, you'd expect the signal to wax and wane with the weather. It doesn't. Not in the way the wave theory predicts. It dips, sure. It varies a bit. But the underlying rhythm, that 26-second tick, refuses to break. Stable through hurricane seasons, stable through doldrums, stable through entire climate cycles. So, if it isn't waves, what else could it be? Enter the second leading theory, championed by a Chinese seismologist named Yingji Xia in 2013. Xia and his team proposed that the pulse isn't an ocean phenomenon at all. They pointed to a volcano. There is an active volcanic complex on the island of São Tomé, sitting almost exactly where the seismic source has been triangulated. Xia's hypothesis was that the heartbeat is volcanic in origin, the slow, rhythmic flexing of the ground around a magma chamber, or pulses of pressure from deep beneath the sea floor, where hot rock is pushing against cold crust. Volcanoes do tick. The old faithful geyser in Yellowstone runs on a similar principle, with pressure building and releasing on a near schedule. If the geometry of São Tomé's plumbing is just right, it could be running its own underground metronome. This theory has a certain elegance. It explains the fixed location, it explains the unusual stability, and there's a real, identifiable piece of geology sitting almost exactly where the signal seems to originate. That doesn't feel like a coincidence. It has problems too. The pulse can be detected on seismometers as far away as Madagascar and the United States. That requires a lot of energy. Volcanic microseisms tend to be local, dying off within a few hundred kilometers. And the rhythm is too clean for most known volcanic processes, which tend to be irregular and stutter rather than tick. Volcanoes can be patient, but they're rarely punctual. So we have two theories, and both are partly right, partly wrong. The community has, more or less, split into camps and started arguing. Meanwhile, the pulse keeps ticking. If you were able to stand on the deck of a ship floating directly above the source, you wouldn't feel a thing. You wouldn't hear it. The waves around you would behave normally. The wind would do what winds do, and the water beneath the hull would keep its secrets. The pulse is far too slow and far too gentle to register as anything to a human body. We only know it's there because instruments designed to detect motion at scales finer than a human hair can record what skin and bone never could. Standing above one of the strangest signals on Earth, you would feel exactly nothing. That, in a way, is the eeriest part. The Earth is doing this right now. And nothing about your daily experience would ever tell you. You walk on solid ground, drive on solid roads, sleep on a foundation of bedrock. And meanwhile, somewhere beneath the South Atlantic, a 26-second clock is keeping perfect time. It was ticking when you brushed your teeth this morning. It was ticking the last time you laughed at a joke. It is ticking right now, while you watch this. And it has not paused for a moment in any of the lifetimes of anyone you've ever known. There are other heartbeats in the geological record, by the way. Smaller pulses, lesser-known rhythms. The Earth has whole symphonies of microseismic noise running underneath it at any given moment. Storm-driven pulses, tidal flexing, the slow groan of plates grinding past one another. A trained seismologist listening to a clean record of the Earth doesn't hear silence. They hear something closer to a whale song, a long, continuous, layered set of vibrations ranging from milliseconds to days. The planet, it turns out, is loud. We just don't have the ears for it. The 26-second pulse stands out because it's so regular and because, after all this time, nothing else like it has been definitively identified. There are similar signals reported in Antarctica and off the coast of New Zealand, but none with the same combination of strength, duration, and persistence. The Bight of Bonny is, as far as we know, alone, which raises a different kind of question. Not what causes it, but why we should care. Microseismic noise used to be considered the trash of seismology. It was the static you had to filter out to find earthquakes. Then, in the early 2000s, scientists realized that this background noise actually contains a treasure trove of information about the Earth's interior. By analyzing how those tiny ambient pulses travel through the planet, you can build a map of the rocks and fluids and structures hidden beneath the surface. The technique is called ambient noise tomography, and it's one of the most powerful tools modern geology has. Think of it as taking an X-ray of the planet using only the hum of its own breathing. A signal as steady and as widespread as the 26-second pulse is, in principle, an enormously useful tool. It's a free, planet-wide ping. If we understood it, we could use it to image the deep Earth in ways that other natural sources can't match. Earthquakes are great for that, but they're rare and unpredictable. The heartbeat is reliable. It runs every day, every hour, every 26 seconds, with no scheduling required. For now, we can't fully use it. We can map it, we can observe its tiny fluctuations, but the engine driving it remains a mystery. The most honest scientists in the field will tell you that. We have theories, we don't have an answer. There's something philosophically uncomfortable about that. We live in a moment where it sometimes feels like everything has been figured out, where the textbooks are closed and the maps are filled in. Then a graduate student stumbles across a 60-year-old signal humming away in the data, traces it to a single point in the Atlantic, and discovers that nobody has been able to crack it. Not the seismologists, not the geophysicists, not the volcanologists. Nobody. Earth is not a solved problem. The deepest hole humanity has ever dug, the Kola super-deep borehole in Russia, reached a little over 12 kilometers down before it had to stop because the rock below was hotter and softer than anyone expected. The Earth's center is roughly 6,371 kilometers below the surface. We have, in other words, scratched less than 1/5 of 1% of the way through our own planet. We have mapped less of the deep ocean than we have of the visible surface of Mars. And every 26 seconds, the planet ticks, and we don't know why. Some scientists have started wondering, quietly, whether the pulse might be the result of something we haven't accounted for at all. A standing wave in the ocean that interacts with a particular geological structure in a way no one has modeled. A slow chemical or thermal cycle in the upper crust. A coupling between the atmosphere and the sea floor that current models don't capture. The honest answer is the one most working geologists give in private. We don't know yet, and we may not figure it out for a while. That's hard for some people to accept. We are wired to want answers, especially about the world right under our feet. The idea that a steady, unmistakable signal could be hiding inside the bedrock of our planet, broadcast for everyone with the right instruments to hear, and that no one can fully explain it, sits uneasily with the way we like to think science works. The pulse isn't just a technical curiosity buried in academic journals. In the last few years, it's become something of a folk story online. People hear about the 26-second tick, and they don't react the way scientists do. They react the way humans have always reacted to mysterious rhythms coming out of the dark. They call it a heartbeat. They imagine the Earth as an organism. They tell each other that the planet is, in some sense, alive. Strictly speaking, that's not science. The Earth is not an animal. It does not have a heart. The pulse is almost certainly a mechanical or geological process, not a biological one. But there's something interesting in the human reflex to hear that signal and immediately assign it meaning. We want the planet to be more than rock. We want it to be a presence. And when we hear something that sounds like a pulse, even one we can't explain, our minds reach for the same word our ancestors would have reached for 1,000 years ago. The pulse, as far as we can tell, is older than humanity's awareness of it. It was thumping away beneath the Atlantic when Jack Oliver was born. It was thumping when Columbus crossed the ocean. It was thumping when the pyramids were under construction, and most likely long before any of those things. We don't know how old it is. We only know how long we've been listening. Somewhere beneath the waves, the Earth has been keeping a steady beat for at least as long as recorded history. And it will keep ticking long after every person watching this video is gone, after the cities are buried, after the languages we speak have changed beyond recognition. The pulse will go on. The planet will go on. And the answer, if there is one, may be waiting for somebody who hasn't been born yet to finally figure it out. For now, we still listen. We measure. We argue. We map the source down to a tighter circle in the Gulf of Guinea, and we run our models, and we wait for the data to give up its secret. It hasn't yet. Maybe one day, a young scientist will sit down in front of a screen, run a new analysis on data that's been sitting around for decades, and finally see the missing piece. Maybe the answer will turn out to be ordinary, the kind of thing that makes everyone slap their foreheads and ask why nobody saw it sooner. Or maybe it will be stranger than any of the current theories. Something in the deep crust we haven't met yet. Something that forces a rewrite of a chapter or two in the geology textbooks. Either way, the heartbeat is still here. It is here right now as you watch this. It is here while you sleep tonight. It will be here tomorrow morning when you wake up. Every 26 seconds, doing whatever it has been doing for as long as it has been doing it. The graduate students will inherit it from the previous generation, the way Greg Bensen inherited it from Jack Oliver. And one of them, eventually, will be the person who breaks it open. Or none of them will. And the pulse will outlast the science, the way certain mysteries quietly do. There is no rule that says we get to know everything. We share this planet with mysteries that have been thumping under the floor the entire time. The Earth is not silent. The Earth has never been silent. We just got lucky enough recently to start hearing it. And we have so much more listening to do. Thanks for watching, and I'll see you in the next one.